The next two videos in this series have to do with radical notation. Let b be some real number. We say that a is the nth root of b when a to the n is equal to b. And when such a value exists, we write that a is equal to the nth root of b. This notation is known as the radical. The number b inside is called the radicand, and the value n is called the index. So for example, we say that 4 is the third root of 64 because we know that 4 to the third power is equal to 64. So we would simply write that the third root of 64 is equal to 4. Additionally, since negative 2 to the fifth power is equal to negative 32, the fifth root of negative 32 is equal to negative 2. It turns out that I can't take even roots of negative numbers, these are undefined as real numbers, but I can take odd roots of negative numbers because these are defined, as we just saw in the fifth root of minus 32 example. So the square root of negative 2 is not defined as a real number, but the third root of negative 8 is equal to negative 2. Another fact that we can observe is the following. The nth root of 0 will always be 0, the nth root of 1 is always 1, and the nth root of negative 1 is equal to negative 1 as long as n is an odd number. Similar to properties of exponents, we have properties of radicals. Start by letting a and b be any real numbers and let m and n be natural numbers. Then, assuming each one of these terms is defined, we have the following rules. The first says that the nth root of a times b is the product of the nth roots of the individuals. The second says that the nth root of a fraction is the nth root of a divided by the nth root of b. And the third says that if I have a nested set of roots, I simply multiply the indices. Note that the nth power of a plus b does not split up like it does in rule number 1. Let's look at a couple examples. First, consider the square root of 16 times 25. This splits up as the square root of 16 times square root of 25, which is 4 times 5, which is 20. Next, look at the cube root of negative 216. I can factor up that negative 216 as negative 1 times 8 times 27. 8 and 27 are both powers of 3, so I can take the cube root of each individual term to get negative 1 times 2 times 3, which equals to negative 6. To motivate our next slide, observe that the fourth root of 16, which can be expressed as the fourth root of 2 to the fourth, is equal to 2. And it seems like I have a cancellation of exponents and indices here. We'll start by saying that it's very tempting to think that matching indices and powers always give you a cancellation. But it's not always the case that the nth root of a to the n equals a. Consider the following. Suppose I'm taking the square root of negative 3 squared. This turns into the square root of 9, which is just 3, but the starting and stopping positions were not the same. It's more accurate to say that I ended at the absolute value of negative 3, which happens to equal 3. Some care needs to be taken because subtle things like this can happen. So, we do have a cancellation law. For any real number a and any natural number n, the nth root of a to the n equals a if n is odd, and the absolute value of a if n is even. The thing about this cancellation law is that it looks harder than it actually is. It's telling us that whenever I have matching exponents and indices, I do get a cancellation. It's just that my final answer might have absolute value bars on them if my index and my powers are both even numbers. But when they're odd numbers, I don't have to worry about it. For our first example, look at the cube root of 27 times y to the third. Both of these are powers of 3. This means that I can reduce 27 back to 3 to the third, and now I have a whole set of canceling indices and exponents. This gives me a final answer of 3 times y. Next, consider the example of the fourth root of 16 times x to the fourth. Like we did before, the strategy will be to see how many powers of 4 I can find inside the radical. I know that 16 can be written as 2 to the fourth power, and our variable x is already raised to the fourth power. So this puts us in good shape for a bunch of cancellations. This means every power of 4 will cancel with the index of 4. However, this is an even valued index, so my final answer is going to look like the absolute value of 2 times x, but thankfully the absolute value of 2 is just 2 itself, so I can express this as 2 times absolute value of x. Again, the overarching strategy here is to try to get every term in the radicand to be expressed as a power that matches the exponent. That's the thing that allows me to use this cancellation law. Let's look at some more challenging examples. Consider the fourth root of 16 times x to the 8th times y. We know that 16 can be written as 2 to the 4th, and we also see an exponent of 8, which is a multiple of 4. So let me rewrite the expression inside as 2 to the 4th times x raised to the 2 times 4 times y. Again, that index of 4 is ultimately what we're chasing. We're trying to get everything inside as much as possible to have a power of 4. Sometimes this means taking a number which is a multiple of 4 and writing it as 4 times whatever. In this case, I wrote 8 as 2 times 4, because again, it reveals that power of 4. We're going to take an extra step and rewrite these exponents to where I have the 4 on the outermost part of the exponent as I can. So we're expressing all these as a power to a power. This makes it a little bit more clear as to which exponents are being canceled and what the final product after cancellation is going to look like. So once I undergo all these steps, I'm going to get the absolute value of x squared on the outside, where that y stays within the radical because it did not have a high enough power to see a cancellation. Because that 2 had a power of 4 and the x squared had a power of 4, those outermost power of 4's cancel, meaning that the 2 and the x squared are what get to escape the radical. And again, because I have an even exponent, I need to tack absolute values on the outside of everything that broke out of the radical. Let's look at another example. Consider the fourth root of x to the 13 times y to the 5th. The difference in this example is that no exponent actually is a multiple of 4, but we can get creative with this. What I'm going to do is actually write 13 as 12 plus 1, and I'm going to write 5 as 4 plus 1. Essentially, I am forcing powers of 4 to be present. The idea is that 12 is the largest multiple of 4 below 13, and 4 is the biggest multiple of 4 below 5. And using properties of exponents, I can split this expression as the following. I'm going to get the fourth root of x to the 12th times x to the 1st times y to the 4th times y to the 1st. Again, I am forcing all multiples of 4 to be present and essentially pushing some other terms that I usually refer to as leftovers off to the side. Now, using the commutative property, I'm going to regroup things a little bit, and then I'm going to also rewrite 12 as 3 times 4. Next, like I did before, all of my powers of 4 I'm going to express as being on the outermost part of the exponent, where everything else is within a set of parentheses. This allows me to take that x to the 3rd to the 4th and that y to the 4th and break them out of the radical. Because I have an even power, I get the absolute value of x cubed times y times the fourth root of x times y. So this is the strategy that I need to use when I have exponents that are not multiples of the index. What I'm trying to do is find the largest multiple of that index less than my exponent so I can additively break up my values. 13 became 12 plus 1, and 5 became 4 plus 1. Again, I'm forcing powers of 4 to be visible. And as we're seeing in both of these examples, my final answers might have some leftover terms within the radicand. And that's not a problem, that's just how some of these solutions come out. For our last example, let's look at one that's a little bit more challenging. I want to look at the fifth root of y to the 30 times z to the 25 divided by 32 times x to the 31. We can observe that almost every exponent is a multiple of 5 except for 31, so we'll get to that in a second. But I can rewrite y to the 30 as y to the 6 times 5. Z to the 25 can be rewritten as z to the 5 times 5. 32, well, that's simply just 2 to the 5th power. And x to the 31, I'm going to write that as x to the 30 plus 1 because 30 is the largest multiple of 5 less than 31. Again, I'm trying to reveal every possible multiple of 5 in the exponents, even if it means I need to additively break up numbers, like writing 31 as 30 plus 1. Let me take that x to the 30 plus 1 and split it down the middle so I can rewrite it as x to the 30 times x to the 1st. This action is just letting me separate the terms whose exponents are multiples of 5 from the terms whose exponents aren't multiples of 5. Now I can use parentheses to rewrite all of my terms inside. I have y to the 6 to the 5, z to the 5th to the 5th, 2 to the 5th, x to the 6th to the 5th, and that x to the 1 that's just kind of by itself. But everything with the power of 5 gets to break out of the radical, leaving me only with the 5th root of 1 over x, and we're done. The thing about radical notation and simplification is that it can be a little bit tricky. Each example does look a little bit different, but rewatch this video as much as you need, look at the type notes, and please reach out with questions if you want to see more examples.